All right. So this lecture, we're going to sort of wrap up the physicsy side of this course by finishing up our primary discussion on the depletion region and surface recombination. Recombination in the depletion region and at the surface. Because last time we talked about recombination in the bulk, which is super important, but perhaps more so is surface recombination. Depletion region can be important because that's where a lot of our photoregenerated carriers are, but just due to the fact that there's that electric field there moving things around, it doesn't tend to happen as much, but still good to talk about. So the recombination rate inside the depletion region is this specific case which comes up in device analysis. So we have to define what we call the recombination or recombination generation depletion region, which is when, let me get a fun color here. We'll do this one, which is when the concentration of electrons is much, much less than what we might expect them to be in like the ordinary situation. Remember that n sub 1 and p sub 1 are constants which are tied to the equilibrium values in the bulk. So what we're saying in the recombination generation depletion region is that n is much, much less than what you'd expect it to, or the concentration of electrons and holes are both much smaller than we'd expect them to be. And similarly, that n times p is less than n sub I squared. In fact, a lot less than n sub I squared. Now, we talked about this last time, that if it's less than n sub I squared, we might expect more generation events to happen, which is what does happen. And we should also note that this is it's not the same as what we have been calling the depletion region in the device, which is where all the dopant ions are, or all the dopant atoms are ionized. So, because in that region, remember at equilibrium, n times p is equal to n sub I squared always, right, in the aggregate. So this is going to be sort of a special case here. And in fact, the recombination generation depletion region has a width which is smaller than W, and it approaches the depletion width at a super large reverse bias, which means that we are making that field stronger and stronger and stronger, right? That field at the interface. So only when we get the field to be super, super strong do we start to get a depletion region, a recombination depletion region that is approximately the size of our device depletion region. Yeah, so that's a little bit of a weird little tangent, but good to note. Now, we are going to take our detail balance equation from last time. We're going to apply these assumptions that n is much, much less than n1 and so on. And we're going to simplify it to get this, which looks pretty simple. It's just n sub I squared divided by those carrier lifetimes multiplied by n1 and p1. It's pretty easy. But then we can make it even easier because we like it when our expressions have very few letters in them. So we're going to simplify it a little bit further. We're going to define a new term, tau naught, which is going to be equal to this mess here. So it's a combination of the carrier lifetimes, both electrons and holes. And we're going to reference that to, so we're going to take the whole lifetime and multiply it by the n sub 1 divided by n sub I. So we're going to take that electron concentration constant and divide it by the intrinsic carrier concentration. And then we're going to do the same thing for the electron lifetime, add them both together. If we do that, the recombination constant for this recombination depletion region becomes very simple. It's just n sub I, which is the intrinsic concentration of carriers, divided by this new lifetime, this new carrier lifetime, tau naught. And that's it. That is it for the depletion region recombination. Pretty simple stuff. Like I mentioned sort of in the notes up here, it does come up a lot in device analysis, but it usually ends up not being that big of a deal. You should also note, though, remember how I said that n times p is much, much less than n sub I squared. Okay, so before, when we had the bulk example, and we put it under illumination under the steady state conditions, we said that n times p is actually greater than n sub I squared, right? And we said in that case, we have driving force to bring us back to equilibrium. In that case, we would enhance the amount of recombination. Well, in this case, we have the opposite situation. So we have NP, I'm going to simplify here, but NP is less than n sub I squared. So now we, again, have driving force to bring us back to our equilibrium position. But this time, we're not adding driving force to recombination. We're actually adding driving force to generation processes. So it's now more likely that we are going to have a generation event than a recombination event, which is why this is negative. Because the rate of recombination is actually negative because we're actually generating more than we're recombining. So in other words, we're making more carriers than we are destroying them. So that's the rate here. And you can sort of think of this as saying, okay, we're going to take the number of intrinsic carriers that we have in any given cubic centimeter. And then we're going to take this tau naught, which is sort of like it's like the lifetime of a generated species, if that makes any sense. And so what we're saying is the rate of recombination, or the rate of generation in this depletion region, is going to be equal to the number of carriers divided by the time for which they exist, the time in which these events happen, right? So like if the tau is 5 seconds, you might expect like one generation event every 5 seconds. So when you take the number divided by the time, you get a rate, and that's what our generation rate is here. So just an interesting note, it actually is going to pop up again later in this lecture. But if we put it together that way, that this is just saying this is the rate of generation in the depletion region, and that's it, pretty easy. Surface recombination is a little bit more interesting. It's got a little bit more going on. In certain cases, it can even be more important than bulk recombination. Because for certain surfaces, maybe you've added a whole bunch of stuff to your surface, and so the reactivity is going to be pretty important. Maybe you have a really defective surface, especially if you have like polycrystalline solar cells. There's lots of different surface interactions. There's lots of surface states that are available to you. And so the recombination events and the way that the charges interact with those states becomes super important. So let's learn about them. So interfacial trap states, or surface states. So these are trap states, which we talked about before in the bulk, which was just like a state that exists inside the band gap that isn't supposed to be there. Like if we had a perfect crystal, that state wouldn't be there. So a surface state is very much the same, except it is localized to a place on the surface. They tend to be continuously distributed within the band gap. So instead of there being like a single trap state in the bulk, where like we have maybe, let's say it's an atom that's missing, right? We have that missing atom, but maybe we have it periodically. And so there's going to be a density of states, but all of those states are going to have the same energy. Here, for the surfaces, they're actually all going to have different energies. So they can be distributed all the way through that band. They aren't necessarily the same energy. So maybe to help you conceptualize this. So in the bulk, we have this one state right there, and there might be like, 1,000 of them. So remember when we were looking into that density of states, like that capital N sub T, which is the density of trap states. So I would be saying that like, oh, well, there's 1,000 of these states, but there's really only one energy at which they happen. And the surface, that's not true. There's actually there's a bunch of energies at which they can happen, And they're also like located all over the place. Now, when we looked at these processes in the bulk, we said, okay, we can have an electron up here. It can be captured or it can be emitted. And then we could have holes that could be emitted or captured, right? And so things could move in and out. And what we were sort of saying is, if there's even one state in the way, like let's say I want to promote an electron from like down here to up here. If there's anything in the way, it might catch that electron. And once you're there, once you have an electron in this state here, you can move it around. And you can jump in between states. Now, at the surface, this is still kind of true. So if I were to take, let's say an electron from here and it's going to pop up. Let's just say it gets caught there and get caught at that energy, right there. So you might expect that it can still sort of move back and forth in between the valence band and the conduction band, right? But because there's all these other states on the way to the valence and the conduction band, you might also expect that this electron can hop here, or it can hop over here, or maybe down there. And there's all these different states that the electrons can go to. In fact, not really. Those trap-to-trap transfers don't really happen. They're pretty rare. And the reason that they're pretty rare is because typically those trapped states, those surface states, are physically separated from one another. So remember when I mentioned that we can distribute over these energies, but it's also distributed in space? Well, these states, let's say call them T1 and T2 for trap 1 and trap 2. In energy, it seems like, yeah, it's super easy. Like there's not a whole lot of energy difference between these states. They're pretty close. We have enough thermal energy. We should be able to move the electron between them. But if you look at the actual system, what you would have to do is take an electron from this individual state and move it way over here, which, if you recall our discussion on tunneling, is going to be pretty hard. These are usually, again, separated by a fair distance. If you were to like calculate the concentration of surface defects, like to give you an idea, 1% is kind of high. It's not ridiculous, but like 1% defects in a surface, that's like a pretty high density of defects. So you can imagine that there's usually pretty good amount of space in between these different states. So the distance makes it harder for the electron to transfer. So in practice, basically you can transfer from one of your bulk states, your conduction band or your valence band, to a trap state, and then back and forth from there, but you can't really go from trap to trap, which is actually quite convenient. It'll make our lives a lot easier. So a couple of conclusions here. The surface states are arranged over a plane, right? They're arranged in space. Specifically, they're arranged over an area because we're only looking at a surface. And so instead of the recombination rate being expressed as like a rate per unit or per unit volume, as we did in the bulk, instead, the rate of recombination here is expressed per unit area. So typically centimeters squared. Also, because the states are distributed in energy all throughout that band, if we're going to get the full rate of recombination, remember I said, like, if, let's say, how easy it is for an electron to get trapped here. Well, what about how easy is it to get trapped there or there or there? You have to sort of sum up the rate at which an electron would get captured by any of those states. And so we're going to integrate it. And we're going to integrate it from the valence band to the conduction band. So we're going to integrate it over the band gap. Because again, that's where those trap states have to exist. All right. So let's get into the math. From our bulk processes last time, we found these recombination rates, Rn and Rp. So review that if you don't remember exactly what these are. And then we're going to just say these work pretty much the same at the surface, but we're going to start playing around with a few assumptions here. And so we're going to start with the overall rate of those electron capture and release, capture and emission, and hole capture and emission rates is going to be given by these expressions. And we're going to put a little subscript S to say that now we're talking about specifically, say, the capture coefficient and the concentration of available states and the concentration of electrons at the surface specifically. These are not necessarily the same values that you would find in the bulk. In fact, this in particular is definitely going to be different because before we looked at a concentration of states as like per centimeters cubed. This is now per centimeter squared. So these are not necessarily the same, but the form of the equation is the same. So we're going to invoke detailed balance again to say that these have to balance each other out. And we're going to get this expression here. We're going to get those N1s and all that. But again, we're going to do this specifically at the surface now. And we're again going to assume some steady state conditions. So again, we're skipping over all the math because we already kind of did it. And we're going to get to the surface recombination rate, which is given here. So it's N times P at the surface minus N sub I squared divided by this 1 over the capture coefficient times the concentration of available states multiplied by this guy again, and similar for the holes. All right, so you might remember last time when we had this expression, I said, well, we have like these constants right here, and it really would be very nice if we wrapped all these constants up into another constant. And turns out they have units of time. And so we turned these into like the time constants, tau. But if you were to actually do the unit analysis here, it actually works out that these are not units of time. These are velocities. So instead of this being like per unit time, this is now like centimeters per second. So if we assume that we're in low light injection conditions, surface bands are flat, we can say like, okay, these are going to be constants. And we're going to call them Sn and Sp. You might remember from last time, we looked at those like big S values, which were like 1 over tau, basically. This is a similar idea, but we're doing little s. And it's going to actually have a velocity component to it. So we can rewrite it like this. And just remember, when you're writing these equations, we have the Sp connected to the Ns and Ns connected to the Ps in the denominator. All right. So we sort of have our detailed balance equation again, specifically at the surface. And then we've adjusted for the fact that we're not working with volumes, we're working with areas. And it turns out that our time constants turn into velocities of recombination. And so we're going to work with those. Okay, so what this is actually, this is just the recombination rate for a single trap state, which maybe you expected because it's the exact same as what we found in the bulk. So this is to get an electron or a hole in and out of a single one of those trap states that exists in the continuum of states inside the band gap. So if we want to get the overall rate, we're going to sum all of them up. So we're going to take this expression and we're going to sort of integrate it over E. We're also going to introduce a new term, which is DIT of E, which is the density of interfacial traps at a specific energy. Note that it's basically the same as the density of states that ends big N sub T, but now we're just doing it as a function of energy and not as just that single state that exists. We're saying there's a lot of different states that can exist, but maybe like there's 2 states at energy 1 and there's 5 states at energy 2, that kind of thing. But similar idea. We can rearrange things. We can get this expression here where the derivative of the surface recombination velocity with respect to everything is going to be equal to this. So these expressions have now changed down here. And we have added this guy over there. Does that make sense? And also, don't forget, this would sort of be like over here. This would be like du dE, but we just multiplied it over. All right. So let's integrate. Let's actually do that integration. So we're going to integrate over the band gap. So we have not R, U surf is going to be equal to the integral from the valence band to the conduction band. So integrating over EG of that expression from above here. This, I don't know about you, I'm not a mathy person. And so this already looks unpleasant to me. But at least, I could say, oh, well, like we got all these terms over here, which I can probably find or solve for. And like, oh, well, really, we only have this di of t of E, and we're integrating over energy. So really, this is the only thing I'm going to have to care about. And that's pretty good. I can integrate over x, like dx. That's no problem. The problem is it's not that simple, unfortunately. It turns out that as a function of energy, a couple of these parameters change, including the n and p sub 1s, and even occasionally our rate constants. So there's like at least 3, maybe up to 5 functions of energy in this expression, which is a lot. So we're going to look into some special cases to simplify things. The first one we're going to look at is low-level injection, which is, again, pretty common assumption. So in this case, we're going to assume n-type. Remember, everything's going to work in reverse, but we're going to stick with n-types. And we're going to say that, okay, the change in concentration for our surface electrons is going to be approximately equal to the change in concentration for our holes at the surface. And that's going to be much, much less than the equilibrium concentration of carriers at the surface. We are also going to assume that the 2 rate constants are approximately equal to each other, which they tend to be pretty close. So we end up with this expression here, where we have our like n times p minus n sub I, which remember is non-zero because we are not at equilibrium. We're at steady state with low-level injection. And we're going to say that's approximately equal to the surface carrier concentration at equilibrium multiplied by the change in our holes, so our minority carriers. And then we're going to take those expressions from the denominator of our big equation, and we are going to simplify and say, oh, actually, we can make this part of the expression a little bit easier. And we're going to say, oh, that is going to be equivalent to our equilibrium value. All right. So again, this is just sort of the algebra going through. I want to go through it so you can see the steps that we're taking and that we're not just doing magic, but I don't really care if you can derive this. I don't think that's important. The concepts are important. So that's going to transform our expression into something that looks pretty nasty. So now we have the surface recombination velocity, which is equal to this integral, this Cp, that should be K PS, multiplied by our density of states. We have this new expression in the denominator, and we multiply the whole thing by the change in the concentration of holes at our surface, or minority carriers at our surface. Fortunately for us, it turns out that this whole thing, that whole integral, is a constant. Under our assumptions here, so under these assumptions that we've put in place for the low-level injection, that whole thing is a constant. And it also turns out that that constant has units of velocity. So we're going to call it SP. So like the recombination velocity of holes, let's say. And that makes this way easier. the recombination velocity is just SP, or sorry, the rate of recombination is just the recombination velocity multiplied by the change in the carrier concentration. Done. Pretty easy. There is also a simplification we can make to the SP term, just as a by the by sort of thing. So if we assume that some of these parameters are approximately constant, we get this crazy little integral for SP, which we simplified down from the previous, from this. So that's been simplified. And it turns out that this would just evaluate to this expression here. There's this EF prime, so the Fermi level prime, which is the energy at which this whole thing is equal to 1, which is approximately the mid gap. It's not super important. I wanted to make sure I said this, but essentially what it's saying is that if you evaluate this at the mid gap, where everything is kind of constant and the same and works out really pretty, you can evaluate this recombination velocity pretty easily. There's only a couple of terms rather than that whole big integral with the denominator and all that. You would just have to reference the Fermi level to this new level where everything sort of works out. So generally in the literature, they just kind of say, all right, sure, technically we had to make all these assumptions that the recombination velocity is going to be independent of energy in certain regions because of these parameters, because of the environment that it's in and all this kind of stuff. But everyone's like, well, we could probably approximate it for everything as this. So a lot of times in literature, you just find that the recombination rate at the surface is just given by recombination velocity times change in the minority carriers at the surface. Strictly speaking, that's not true. You have to say that we're making these assumptions, and that doesn't always work, but it works like most of the time. So just be aware that if you see this in the literature, check their assumptions, make sure that this is actually something that they could apply. So just make sure that you're aware of that. All right, so that's special case number 1, is saying we're low level injection. The other special case is, what if we're at a depleted surface? So in this case, we have that the surface concentration of electrons and holes is basically nothing. In that case, the recombination rate simplifies considerably. And again, once again, this whole thing is just a constant. And it's a velocity constant again. So we're going to call it S sub naught, which is the depleted surface recombination velocity. Or notice we have a minus sign. And notice we're at a depleted surface. So if N and P are both approaching 0, that means they're probably going to be a lot less than N sub I squared, right? Which means that we are in a region, and it kind of makes sense because we're saying it's depleted. We are in a region in which we are actually going to get more generation processes than we get recombination processes. So in that case, we have a minus sign here because we're looking at a recombination rate. So the opposite of that is the generation. So that S sub naught is sometimes also called the surface generation velocity. So that simplifies down to this. Again, look, it's very simple. It's just the surface generation velocity multiplied by the concentration of intrinsic carriers. You can also calculate this with this sort of expression down here. But the big takeaway here is that if you've depleted your surface, now you're actually going to get more generation processes, and you're going to solve it by this generation velocity multiplied by the intrinsic carrier concentration, where for a low light injection or low level injection, you are going to have the recombination velocity be basically a function of the recombination velocity for whichever thing you're using, either holes or electrons, multiplied by the change in minority carrier concentration. All right, I know that was really mathy. So let's talk about the takeaways here. Takeaway number one. So in the depletion region, so in the depletion region, which remember for recombination and generation is smaller than our normal depletion width, we are going to get a generation process which is given by a relatively simple expression. I'm not going to rewrite it here, but we talked about it. And that it's important for devices, but generally doesn't like happen a lot because the carriers move too quickly. 2, at the surface. So this, we have states spread out in energy and space. We know that the basic recombination, so we add up all rates, and that is non-trivial. That basic equation, remember, is not the easiest thing to solve. But with some simplifications, so in low-level injection, everything sort of works out so that U is equal to that the carrier lifetime. I'm going to say SP times the change in our surface minority carriers. And in the depletion approximation, U is going to be equal to minus, it's a generation process, right? Generation, S sub naught times N sub I, our intrinsic carrier concentration. So that's going to wrap us up here. In the next few lectures, we will talk about some of the concepts introduced in the problem set and also look into some actual photoelectrochemical literature and see if we can understand what's going on, see some cool advances in the field and how our class can apply to that. So I will see you in the next lecture.